Okay, good afternoon, everyone. So my name is Lucian Covaci, as you heard, and I'm going to talk to you today about these flat bands and correlated states in bulk of graphene superlattices. And I come from University of Antwerp, which is in Belgium. So just a short outline, I will maybe introduce for people that are not aware of the effect of strain in graphene, just brief theoretical introduction, and also show you some of the experimental evidence for the large pseudomagnetic fields that has been observed over the years. And then I'll just start with these STM experiments on buccal graphene, these recent experiments where we saw the appearance of a periodic strain structure and flat electronic bands, and even the evidence of correlations and induced gap. And I will finish with an outlook for strain-induced flat bands, relevant strain configurations, and prospect for enhancing correlations. So, but indeed, as Mira said, the previous talk is actually very relevant here. So it would be nice if there's a future collaboration in this direction, because we need to know more about that, how to manipulate these strain configurations. And at the end, I will, if there is time, I'll advertise these tight binding codes that we have, which might be of use for some of you. Okay, so the main motivation, of course, for this mini workshop is the strong correlations in 2D materials or graphene. And of course, you want to decrease the ratio between kinetic and potential energy. And one way to do that is to induce flat bands or to localize the electrons. And over the years, there have been various ways to do this. Just use strong magnetic fields and then consider interactions in Landau levels. So you create fractional quantum Hall effects, Wigner crystals. Or as we've heard previously today, if you just have the surface states of rhombohedrally stacked n-layer graphene, or for example, three-layer graphene, you have k-cube dispersions. So near the Dirac point, you'll have increased relevance of the potential energies. And of course, also we heard today this very hot topic on Moiré physics in 2D van der Waals heterostructures, which of course started with the magic twisted bilayer graphene, which now is more than double, triple, and so on. So there are so many combinations that are very exciting these days that experimentalists are able to do such experiments. And then you also have this ABC stacked trilayer graphene aligned on HBN substrate, where the periodicity of the Moiré would modify again the low energy band structures, induce topological flat bands with relevance to superconductivity and insulating states. And also there is another possibility to combine, for example, in this trilayer, where you can encapsulate graphene between two HBNs that are very slightly misaligned. So then combining the Moirés of the combinations, you would get some low wavelength Moiré, which modifies the low energy structures. But actually today I will talk to you about the new platform, which is the periodic straining in graphene, which is not that new in terms of the theoretical aspect, but experimentally this has been realized only recently. And you can actually read after my presentation, you can read all about it in this recent paper. So for people who are not aware of the effect of strain in graphene, I will just introduce the pseudovector potential and pseudomagnetic field. Well, of course, everyone knows the graphene dispersion relation. And of course, it starts with this single pi electron on the carbons. And once you apply strain, you have to consider some modifications of your tight binding Hamiltonian. For example, here, let me just. So once the simplest way here is just to consider the change in the hoppings, which can be either as a function of the distance between the carbon atoms or some curvature or a combination of those. But you can identify some quantity with A of R, which actually tells you how these hoppings change around the unit cell. And so this is related to the change in the distance between the carbon atoms, but also change in the hoppings. So in the low energy approximation, as was shown, okay, I don't have the citation here, but I guess most of you know that, as was shown by Gaim and Guinea in 2010, that in the low energy approximation and in the low strain and near the Dirac point, you can show that this modification, this perturbation of the Hamiltonian acts exactly as a pseudo-vector potential. And the pseudo-vector potential can be directly related to the strain tensor. And for uniaxial strain, of course, this was just a constant. So you just shift the Dirac point in the Brillouin zone. But in the case of inhomogeneous strains, you can imagine that something like a magnetic field can be calculated, which depends on the derivatives of your vector potentials. And the question is, of course, that you can also find Pseudolandau levels. And as proposed in 2010, you can have this kind of trigonal deformation of any graphene lattice. So for example, here you have a graphene hexagon where you pull from 3 sides, and this just shows the deformation of the flake, but also in color is the magnitude of the induced pseudomagnetic field. And to get Pseudolandau levels, you need regions with the constant or almost constant field that are as large as the cyclotron orbit. And that is the case here. So if we plot the local density of states in the center of your hexagon as a function of strain, you start seeing the appearance of peaks that scale like square root of n and look exactly like Landau levels. But different from Landau levels, you actually see a strong sublattice polarization in the zeroth level. And that is because the pseudomagnetic field or the strain do not break the time reversal symmetry, but instead break the sublattice symmetry, and that allows you to have these gaps that are induced in graphene. So these were confirmed already from 2010, and this is a well-known experiment from the group of Chromi, where they have deposited or they grown graphene on platinum-111, and it spontaneously forms highly strained nanobubbles. And by doing STM spectroscopy, and they actually found this square root of n dependence of the peaks, and they extracted pseudomagnetic fields as large as 400 Tesla. And then since then, there are various other ways of generating inhomogeneous strains. And as you've heard in the previous talk, you can use pillars, you can change the density of the pillars, the heights of the pillars, and you can take advantage of the fact that graphene might attach to the substrate, and that will induce some strain profile between the pillar and this attached region. You can also use the STM tip to pull the graphene sheet itself. If it sits on top of some hole in the substrate, you can pull, but at the same time investigate electronic properties. And recently, in the group of Andrea Damascelli, they've grown graphene on silicon carbide, where these triangular pits form again spontaneously. And with ARPES, they were able to see the Pseudolandau levels forming in these triangular pits. So let me switch now to the experiment that is of interest here. So this was done by Eva Andrei at the University of Rutgers. And it starts with just depositing graphene on a substrate, which here they use niobium diselenide or also poronitride. So so far nothing special. But in their experiments, they actually, when they do the STM measurements, they see that in some regions of the sample, they have this regular linear dispersion, but in some regions, something peculiar happens. So they see peaks, which resembles Landau levels or Pseudolandau levels. And if they track, for example, the STM topography at an energy related to, let's say, one of these peaks, they see this beautiful superlattice of a feature of superlattice. So our simple explanation here is that inevitably wrinkles appear. So, and they also they have that STM topography on a larger scale, and there are some wrinkles similar to the ones shown in these figures. So wrinkles inevitably appear, and in their typical thermal annealing, then due to the difference in the expansion coefficient between the graphene and the substrate, this leads at some points to some compressive forces coming from these wrinkles. And that would induce at some point some buckling instability in the graphene, which would result in these spontaneous periodic strains. So in addition to this nice two-dimensional triangular lattice, they also see one-dimensional features or hybrid features, which are 1D or 2D. So just to go further into these measurements, so they also did STS measurements at different locations on the sample. So for example, if you plot the di by dv at one of these crest positions, so it's at the top of the mountain, they see this sequence of peaks that scale like square root of n. But if they plot the STS somewhere in between the mountains in the valley, then they see the sequence that depends as linearly with n. And another clue here is that if they do a high resolution STM again at the top of the mountain at the peak or in the valley, they see a valley polarized spectra. But the polarization is in the different sublattice, and that can be seen if you actually scan the spectrum, scan the sample somewhere in the intermediate regions. So in those regions, they can see a transition between the one sublattice to the other sublattice. So these all point out towards the fact that we have some strong pseudomagnetic fields, and these states are related to indeed to Pseudolandau levels. So to elucidate further, we did a simulation of a periodic pseudomagnetic field lattice. And here we just took this triangular lattice formed by the sum of these three cosines, and we can nicely match the periodicity seen in the topographic feature with our model. So then after some long calculations, you can plot the local density of states as a function of the strength of the pseudomagnetic field. And this is plotted at the crest position. So here you can see this strong sublattice polarization in the zero Landau level, and this increasing gap as a function of pseudomagnetic field as expected. But interestingly, in the transition region or in the valley, in the trough region, there are different states that appear, which actually do not scale like square root of n, and they live in this region, energy region, which is actually the gap in the crest. And so we can actually identify some effective energy, some effective field, which would give us some energy gap that matches with the energy gaps seen in the spectroscopy. So as we do that, this is plotted here. So this is just a cut of the previous plots, but at the field of 112 effective Tesla pseudomagnetic field. And we can nicely see the square root of n sequence and the match with the experiment in this sense. But in the trough region, we see similar to the experiment, this linear dependence on the index. And on the right graph, this is an LDOS map along a line that is shown here. So it goes from one crest to the other crest. So here you can see actually all the different types of spectra. This the one where you have only Pseudolandau levels, and the transition, and the valleys where you have linear dependence. So the fact that the features here do not depend on the square root of n leads us to believe that this is not related so much to the strain in graphene, but is more related to some confinement effects. And so if you imagine that you have some kind of parabolic potential here, so the electrons cannot go in the strong field regions because these are gaps, so they'll just be reflected. You can identify some relation between this energy difference here and the width of your potential well. And for the energy gaps of around 90 milli-electron volts, this number comes out to be around 20 or so nanometers, which actually matches with what is observed experimentally this period of the topographic features. And I also promised to show you some flat bands. And so that's what we show here. So this is just a dispersion across a path in the mini Brillouin zone defined by the triangular lattice. And so you can see two types of bands here. So this band at low energy at the Dirac point, which is just some kind of renormalization of the previous Dirac Dirac spectrum, but you now also see these states that are related to this confined states. And if we compare the STS map, so the DI by dV map from the experiment at different energies with the local density of states map that we calculate, we can nicely see some correspondence in the sense that this low energy band is localized at the crest regions, while these other energy bands are always localized in between the crest regions. Okay, and there is also evidence of correlations, induced gaps, but not in the graphene on niobium diselenide, because they were not able to dope the graphene there. But instead, this is on graphene on HBN. But the structure is slightly different, but still we can see the Pseudolandau levels in the crest region, but in the trough regions, there's no such Pseudolandau levels. But as you dope the graphene across the Pseudolandau level, you can see that some depression or a gap, or even a depression or even a gap appears in the DI by dV, which is clearly an indication of strong correlations that are important in this case. But yeah, there's a lot more work to do in this direction. So this is just, let's say, a first step showing that this would be an interesting direction to continue. So also along the same lines, now the question is, how flat can these bands be? So this is the same profile that I showed you before of the pseudomagnetic field. And as I plot the band structure for different strength of this, the constant in front of this, some of these three cosines, you can clearly see that the bands become flatter. So you just identify here this delta E1, E2, E3. So if I plot this as a function of the strength of this pseudomagnetic field, but also the period of the superlattice, the color bar is the magnitude of these different bandwidths. And the white line here, or the black dots, is some critical bandwidth, which is related to some characteristic Coulomb energy given by this periodicity here. So clearly you can easily go with the bandwidth to be much smaller or much smaller than some characteristic Coulomb energy, and there's room for tuning all the different the bandwidths. So you can have a choice of which of these bands you want to dope. But also for the lowest energy band, as I said, this is just a renormalization of the previous Dirac points. You can also identify some strong changes in the Fermi velocity. So here the color bar is the Fermi velocity, and the dotted points are the percentage of the initial Fermi. So these are critical lines for the percentage of the original Fermi velocity. So for example, here you have just 1% of the previous, of the original Fermi velocity. So again, you can have different types of buckling modes. I didn't really explain that, but this actually connects with the previous talk. So that's why I said that we need to know a lot more in this direction. So there's a combination between this elastic properties of the membranes, how you can generate buckling modes and how you can control them. But here we identified two buckling modes, and one of them is the so-called hexagonal mode, which appear, so these buckling modes appear, are metastable modes appearing when you compress elastic membrane. So this is the hexagonal mode, and the color bar here is the height of the deformation. So now you have some kind of Gaussian bumps. And this translates into a profile of the pseudomagnetic field that oscillates. So it's a slightly different configuration, but still, if you plot the local density of states as a function of the height of this deformation, which would translate into a different magnitude of the pseudomagnetic field, you find these flat bands appearing. And another mode, which is in some cases even the lowest energy mode, is the so-called herringbone mode, which is a kind of quasi one-dimensional, but still you can find that the field oscillates around this deformation. So again, you'll form these flat bands at some point. But nevertheless, the one that is...
So sorry to interrupt. We're just we're out of time. So if you
so I was just want to see
great
summary. I will just leave the summary here. So maybe there are questions, and acknowledge the collaborators and the funding. So maybe to have questions rather than me saying the summary. So thank you very much.
All right. Thank you. Thank you for a great talk. We have maybe time for one quick question. Anyone would like to ask a question? Milorad?
Maybe not a question, but to give a chance to Lucian to say something about those codes, which I think are useful.
Yes, so the codes, so we have two sets of codes, one called pi binding, one called kite. And these are tight binding codes where you can model almost any type of tight binding Hamiltonian that you want, but more interestingly, you can model easily disorder and also different types of disorder, from on-site disorder, charged impurities, spin flips, and so on. And we can actually calculate a number of different observables in our codes as optical conductivities, DC conductivities, densities of states, and so on. But we can do that for large systems, which means that we can reach some experimentally relevant regimes where the defect density is not that high. So yeah, it's that's where the strength is, that we can do very large systems with different types of disorders and with magnetic fields. So if you're interested, either contact me or visit these sites, but yeah, you can just contact me and I will point you out towards where to look.